Assalamualaikum warahmatullahi wabarakatuh, and very good morning. Alhamdulillah, I would like to thank MACE, Malaysian Automatic Control Engineer Society, give me opportunity to share in this technical talk. I am Maziyah from Faculty of Electrical and Electronics Engineering Technology, University Malaysia Pahang. Inshallah, today I will share on sliding mode control design strategy. I believe many of us familiar with this sliding mode control. I hope this sharing will benefit to some of us who still looking for how to design a controller using sliding mode control. Okay, I will start my presentation with introduction to sliding mode control. I will focus my design strategy for continuous time sliding mode control, and I will share on ways of chattering reduction, and also I'll share how we can use more than one ISMC strategies to design a controller meant for chattering reduction, and also to improve the performance of the controller. Finally, the conclusion. Okay, this ISMC was introduced by Omelianov and his co-researchers, including Atkins and Itkis. They are from Soviet Union at the time, in early 1950s. So basically, it was started with variable structure control for varying system structure for stabilization. So after that, this algorithm has promoted interest among control researchers since this ISMC is insensitive to disturbances and also robust against parameter variation. So basically, this ISMC is a robust control technique. We can define this ISMC as a motion of the system trajectory along a chosen line or hyperplane or surface of the state space. So when we design this ISMC, we always have two control objectives. First one is we want to drive the nonlinear plan state trajectory onto a specified and our chosen surface in the state space, which call sliding or switching surface or sliding manifold. And second one, we also want to maintain the plan state trajectory on this surface at all subsequent times. So these two objectives always need to be laid out when you want to design SMC. What advantage offered by this SMC? First is the dynamic behavior of the system may be tailored by the particular choice of sliding function. So we can choose our sliding surface that tailored to our application, and also the closed loop response becomes totally insensitive to some particular uncertainties. The disadvantage or drawbacks of the SMC is chattering phenomena, or we call it as an undesired high frequency oscillation due to the discontinuous switching function that we use, which is signal, which causes the signal to oscillate around the sliding mode surface. So this is the ideal. study mode, and practical of study mode always come with shattering, okay, at this sliding surface. So this is the overall system dynamics given by this equation, where this entire dynamic of the system is governed by our line or surface parameters only. So this is the case if we design our controller for regulation problem. So in sliding mode, dynamics is dependent of system parameters. So in our sliding surface, we don't have any system parameters. So it is robust. So robust, the requirement when we design this ISMC actually is we want our sliding surface reaching towards the sliding surface in finite time, and we able to maintain the sliding mode for all future times. So these are the two requirements. Then only we can achieve the objective of this SMC. Okay, because we want to drive the nonlinear state trajectory into the specified surface, and also we want to maintain. So in order to achieve this, we have to fulfill these two requirements. So the first requirement, which is reaching phase, design a stable surface. We need to design a stable surface. So this reaching phase is the part where the describing point starts from its initial condition and moves toward the sliding surface. So this is very important in this phase. During this period, however, the tracking error cannot be controlled directly, and the system response is sensitive to parameter variation and noise. So this is during the reaching phase. How we can design a stable sliding surface? So the stable sliding surface should be is stable if it is a Hurwitz polynomial in most cases, meaning unstable sliding mode is not sliding mode at all. So we have to have a stable sliding surface to make sure our sliding mode exists. Otherwise, it's not exist at all. And then sliding mode should not take forever to start, meaning it has to start in a finite time, and sliding mode enforce is necessary. So we can design our sliding surface maybe either linear or non-linear. It's up to us. So the second phase is sliding mode phase, where we design our controller to force the system states onto the chosen sliding surface in finite time, which is we want to accomplish the objective number 2 and also the requirement number 2. So this is the phase in which the describing points moves on the desired sliding surface, and also in this phase, the describing point does not necessarily follow any system trajectory that was present in the original fixed input system, and this is because the sliding surface, the input continuously switches, and the system description is essentially discontinuous. So this is how we hope our SMC works. Okay, we should start somewhere in reaching phase, and it has to reach the sliding mode phase. Okay, it has to reach the sliding mode phase during finite time. Okay, so as I mentioned earlier, our design strategy is concentrated on continuous time, so I will not touch on discrete time SMC. So this is a second order nonlinear system given by this equation. So this is already in canonical controller canonical form. So in reaching phase, we design our surface. We can define our sliding surface as this, and this is the general form of sliding surface, depend on what order of the system that you are controlling. So in this case, our system is second order, so the sliding surface will look like this. And then since this design is for tracking problem, okay, so for tracking error, we define the tracking error as E, which is actual state minus the desired or the set point. We can define this either the desired minus the actual or the actual minus desired, so it doesn't matter. Okay, so we have to choose the constant or positive constant C such that the stable sliding is achieved. Then if the sliding surface is designed as the system dynamic confined to S to equal to 0 is stable, then we meet the requirement number 1. Okay. In sliding mode phase, we define our control law as this. So in SMC, for conventional SMC, this is the standard way we define our control law, which is the equivalent control part and also the discontinuous control part, or maybe some researcher call this as a switching part. So it means the same. Okay, so we can define our equivalent control when the derivative of our sliding surface goes to 0. When this goes to 0, we rearrange so that we have our equivalent control equal to this. Okay, so then we can define our switching control law or discontinuous control law by choosing one of these reaching law. Either we can choose constant rate reaching law, constant plus proportional rate, or power rate reaching law. So we can define which one that we want to use. The convergence or reaching to S equal to 0, this sliding mode should start at a finite time so that we can fulfill the requirement number 2. What means by this requirement? Meaning the sliding mode should start and it should start in finite time. Then only we can fulfill the requirement number 2. To be sure that the sliding mode starts at time t greater than 0, irrespective of initial state of x at t equal to 0, then we should make sure that the state trajectory is always moving towards s equal to 1, and whenever s is not 0. Okay, so this is very important. And the other requirement, not the other requirement, this sub of the second requirement is we have to make sure that we have to define our Lyapunov function. Lyapunov function can be used to check the stability of the proposed controller. In our case, we define our Lyapunov function as half s squared, and the dynamics or the derivative of the Lyapunov can be defined as time s dot is positive, negative, definite. This is what we call reachability condition. Okay, so however, the convergence only is not sufficient. So we have to find another strong condition so that we can ensure the finite time convergence. So this is not enough for requirement number 2, so we have to define the eta reachability condition, which is eta of S, where eta should be greater than 0. So then only in this case we have finite time convergence. In order to ensure the reachability, as I mentioned earlier, so we set our Lyapunov function as half S squared, and its derivative when we compute, we will get this, and we get the partial derivative of this equation that I have shown you previously, and then from this we can have our equivalent component. Okay, then we choose our discontinuous control or switching control as a constant rate. K sign should be minus this one. And the same way we apply this derivative Lyapunov function, and we end up with this, where we have to ensure that our K should be greater or equal to mu and must be positive definite. So the overall ISMC control law for conventional control law can be written as this for the, in this case, in this example. Okay, so as I mentioned earlier, ISMC drawbacks or disadvantage of ISMC is chattering. So how we can reduce, or we can attenuate, or we can suppress this chattering? Okay, so theoretically we know that switching causes zero magnitude oscillation with infinite frequency in X. However, practically it's not, because all the practical or all the mechanical part, there is a limitation. So this is we call the undesirable phenomena, which is chattering. Okay, so high frequency of chattering actuates unmodeled high frequency dynamic. Okay, with this we will deteriorate our controller performance because of this chattering. So how we can reduce, or we can attenuate, or we can suppress this chattering? One of it is by using smoothing approach, or some people may call it as a boundary layer, and also called as a quasi sliding mode control. So what we do in this approach, we replace our signum function with this saturation function. Okay, or we can replace with tangent hyperbolic, or we can replace with this equation, or eta is considered as a epsilon is a small positive scalar. And when we have a boundary layer, what is meant by boundary layer? There is our trajectory is move around this boundary layer that we have set. So this will result in slower sliding dynamics, and we might lose our sliding mode. So when use this approach, we have to be careful so that we don't lose our sliding mode. So using the previous example, okay, so the design for equivalent control remain the same as previous. However, now the discontinuous control law can be replaced by this, either one of these three. In this case, I choose the signum to be S over absolute S plus epsilon. The other way to reduce the chattering is using integral sliding mode, ISMC, where in this ISMC we establish sliding mode from the very start of the process, meaning to say that we have in ISMC also known as no reaching phase sliding mode, and chattering phenomena we consider reduced by through this approach, and we enhance the robustness as compared to conventional sliding modes. This system involves a full state in sliding mode, meaning there is no order reduction occurs, and we have to put extra push and driving control component is required to direct the system dynamic. So we have this nonlinear system. We assume that this B has full right, meaning this system is fully controllable, and the system is controlled by a suitable control law U, which is U naught, with this dynamic. When this system perform very well under U naught. Okay, so however in practical we always operate under uncertainty, so that's why we have to include our uncertainty in our system dynamics, where this HXT is represent a match uncertainty. So in this case we design mesh controller with match uncertainty. Okay, where since it match uncertainty, so this H should be element of span of B or equivalent to this, and it has a limit. Okay, this uncertainty has a limit. It always has to be smaller or equal to the maximum of the uncertainty. Okay, what is the control objective for this ISMC? So basically we want to design a control law such that all the trajectories of the uncertain system satisfy this equation from the initial time. Okay, from the initial time. Then we define our control law as U naught plus U1, where this U naught is actually the operate when the system without any perturbation, then the system is controlled by this U naught as mentioned here. Okay, so for the system without perturbation, then we use this U naught to control our system. And then we use equation 4, and then we substitute into equation 3. Then we will have this equation. We have two portions, which is one is driven by this U naught and the other part is by U1. And then after that, this is then we define the sliding manifold or sliding surface as S naught plus Z, where this S naught actually can be defined as conventional SMC sliding surface. Okay. Then the time derivative of the sliding surface is given by this equation, and then when we know that we have our S naught is equal to the conventional sliding surface of conventional SMC, then we have this, and from here we can choose our Z dot such that then okay, so we choose this z dot as this, then we will have our equation left with this equation. Okay, and then the dynamic of the system in sliding mode. Okay, so we have our u naught here, and we can define our u1, which enforce the sliding mode takes the form of this form. So again, we can choose any type of reaching law. This is the constant rate reaching law, so we can use this. And now we substitute this equation 8 and 9 into equation 7. While finally what we will have actually in this equation shows that the uncertainties will be rejected only if this partial of the gradient of S naught is full right. Okay, so we have to make sure that our B is in full right. Again, if we want to enforce on the strong reachability, we have to satisfy this equation. And again, in practical implementation, the control will appear as this: u naught plus u1 eq, and the equivalent value of this continuous control is equal to average of value b as a first order filter of the form in this form. So this is quite detailed explained in paper in the reference that I show in the reference section. So with this, we have the worst case where we have Chatria suppressed to the tolerable level. It's still there is chattering there, but now we reduce it. Now to help us to be more understand on this ISMC, so I choose this example. Again, this is the second order nonlinear system. So we have this control law for ISMC defined as u naught plus u1, where this u naught actually can be defined based on linear feedback control law. For example, pole placement. So we can use that to control the system when there's no uncertainty in the system. And then we define our sliding surface or sliding manifold as this. Okay, so as I mentioned earlier, our S naught is defined based on conventional ISMC. And then when we substitute into this equation, then we will have this equation. And then the derivative of our sliding surface, okay, we will have this. And then we can choose our Z dot become like this. And finally, when we substitute this Z dot into the equation, we will end up with this. Where we know that the U1 is basically equals to U equivalent plus U discontinuous, where we can define our U equivalent when our sliding surface, the derivative of sliding surface equals to 0. In this case is our U equivalent control is equals to 0. However, in some cases we may not have 0 equivalent control. We will have something on U equivalent. So it depends on the system, or it depends on our choice of our Z dot. Okay, and now we can define our discontinuous control U1 switching as a conventional reaching law. In this case, I choose as a constant rate. Okay, and then we equate to this equation. Okay, finally we will end up with this. So the overall ISMC control law now can be written as U0 plus U1 equals to, this is the portion of U0 and this is the portion of U1 where we don't have the equivalent control portion. So basically, when we want to use this as an ISMC, we have to check the controllability and we have to convert the system into controller canonical form or regular form, and we have to construct the controller for the idle system, which is when the system under controlled by U0, and then we construct the integral manifold, then we construct the overall controller for the ISMC, then we check the closed loop stability. Finally we can simulate what we have designed previously. So that is as an ISMC. The other way to reduce the chattering is using higher order sliding mode. So the good about higher order sliding mode is it establishes sliding mode in finite time, and also not only that, finite time convergence, it also results in high precision, meaning the accuracy or the steady state error is improved, and the chattering reduction occurs to tolerable without loss of robustness. Okay, and all the sliding mode features are maintained. The only problem is that the design of higher order SMC is not straightforward, not like first order sliding mode, and the complexity is increases from case to case. It depends on what is the plan that you want to control. Okay, so these are the higher order for R up to 5. So the one that I put in the box is actually the most frequently used. The first one is the first order, the second one is the second order. Okay, so I will concentrate on the second order. So these are the standard sliding mode, second order sliding mode control. It include twisting controller. Okay, we also have the terminal sliding mode. We have suboptimal, we have super twisting, and we have a few others. So however, in this example, I just show on super twisting. Okay, so again, why this second order is more popular compared to others? Because this is applicable to the system of the relative degree of 2. Input appears in second derivative of the function, and input is still discontinuous. However, this is important, there is no chattering in state. Okay, so this is the good features of higher order sliding mode control. So I will show the super twisting in the next section, which is hybrid SMC design. Why we need this SMC design? This is another way of reducing chattering. Okay, so basically in this hybrid, we can integrate maybe 2 or more SMC strategies, and also we can combine with other control strategies like backstepping, or maybe on intelligent kind of control like fuzzy, or maybe neural network. So it depends on us what we want to design, what are the strategies that we want to use for our controller. So in this case, I'll show two strategies, two SMC strategies being integrated, which is ISMC and super twisting. Again, the objective is just we want to reduce the chattering, and also we can improve the performance of single SMC strategy. Later we can see the improvement single SMC as compared to hybrid SMC. So since SMC is known as no reaching phase, and we know that super twisting is good in convergence in finite time, so meaning our approach, we will have the result in no reaching phase and convergence in finite time. So this is very important. Okay, the same example we use. Okay, so the controller is defined as ISMC controller, which is a U0 plus U1, and all the steps after this is following the ISMC strategy, design strategy, except now our discontinuous control is defined as super twisting reaching low. Previously we used a conventional reaching low, now we use super twisting reaching low. So we have overall ISMC plus super twisting, or we call it ISMC, or any name that you want to name it. Okay, this is the portion of U0. Okay, so we don't have U equivalent, we just have U discontinuous. Okay, so maybe it looks like a little bit different as I showed in previous slide. It just a little bit twist, where in this part, okay, you have U2 dot. Okay, so how we can get this U2? By integrate this equation. So this is what I did here. Okay, so P normally from the papers that I referred, most of researchers choose P as 0.5. K1, K2, beta 1 and beta 2 can be varied until we get a satisfying performance. Okay, so now I want to share some of the simulation results. So you can see here, okay, this is output X1. Okay, the red one is we have a SMC. Okay, blue one is the QSMC. Okay, we have ISMC, we have super twisting, and finally the integration between ISMC and super twisting. Okay, I zoom into this line. Okay, when we look at this ISMC, okay, there's still chattering there. However, for super twisting there's no chattering, and for super twisting alone, it still have, we call the reaching phase, and for ISMC plus super twisting, so we remove that reaching phase. Okay, so this for control input. Okay, so basically we don't have any chattering for ISMC with super twisting. Same goes to sliding surface. So these are the things that we can do to reduce or to suppress the chattering effect. We can try other combination to see the improvement. And as a conclusion, so basically have shared on the basic design of conventional SMC. It always involves two steps. Step one is to design the starting surface, the stable starting surface, and then we design the controller such that we can reject the perturbation or disturbances. And then we move to this SMC design for shuttering reduction, which is we use the boundary layer, ISMC, and also higher order. And finally, we see the improvement on shattering by integrates two different SMC strategies. In this sharing, I share on integration of integral study mode with super twisting. Okay, with that, I hope this sharing will benefit some of us, and that thank you very much.